This video is brought to you by Iona, North America's premier charging network. With unmatched commitment to elevating the customer experience, Iona is opening America's roads to all EVs, giving drivers the coverage they need, the reliability they deserve, and the amenities they crave. Hello and welcome to another Out of Spec Reviews video, and welcome to the first ever episode of what I'm calling EV Inbox. This is where you guys will submit your questions either through social media or through comments on our videos, asking interesting questions about electric cars. And it seems that there is obviously, like with any topic, a broad level of understanding that varies based off of our viewer base. And through this series, I hope that we can all learn together and get everyone a little bit thinking deeper about electric cars. I don't really want to get into the how far do they go on a charge or how long does it take to charge. I want to answer some real nerdy questions through this series. And in this episode, I have picked your top 7 questions based off of engagement to a post that I made on social media. And we're going to basically rapid fire answer some of these questions. So again, leave the topics you're interested in the comment section of this video. We have a fantastic viewer base that really are experts. Many of our viewers are insane experts, many of whom work for automakers or charge point operators or charging manufacturers that chime in often and help answer questions as well. But through this EV Inbox series, I really want to make it as educational as possible. So let's go through and answer your top 7 questions that you guys left me about electric cars. So of course I could probably make a 1-hour long video about every single topic here that we talk about, which I'm not going to make you sit through in this episode. And another thing I want to reference to you guys is if we don't get to your question or if you want further explanation about a particular topic that we're discussing, put it in the YouTube comment section below. One of the coolest things about our Out of Spec Reviews channel is our amazing viewer base. And there are so many folks here watching this video and engaging in our comment section that work for automakers, that work for engineering firms, that work for charging companies, whether it's hardware or charge point operators. And so there's so many in-industry folks here and engaged with our content that I'm sure if you ask a question down below and someone knows the answer to it, they will help you figure out certain topics. So let's run through the top 7 questions that we got based off of a recent social media post from my side. And our first question actually comes from my colleague Colton. I sorted them by level of engagement to each question, and his question had the most engagement. Colton asks, what are the advantages or disadvantages of an 800 volt system architecture? So Colton is discussing, like, if you're in an automaker position where you're designing or developing a new electric car, why would you choose to go 800 volt system architecture? Now, keep in mind, this is a fairly early decision in the development process, and there's really a couple different ways. Well, there's many different ways, but a couple main different ways that an automaker would have to think about this. The first is, are you making a one-off model that potentially is a bespoke platform with no real sharing in terms of architecture? Or are you making a scalable architecture that will underpin vehicles from small sedans to large SUVs and sports cars, which has really been the trend in the electric car world to go with a skateboard-like flexible architecture, but with similar electrical systems and ECUs and chassis design elements, things like that. And in general, you kind of make that decision early on in the process, of course, because there's so many advantages and disadvantages to going 800 volt. And I'm going to give you 2 or 3 advantages or disadvantages, but of course this really needs a full dedicated video from my side. So if you're interested in that, I'm happy to go deeper at some point. Let's talk about the disadvantages of going 800 volt in terms of your system architecture. The first and probably easiest answer you'll hear to this is cost. Well, it's going to cost more. And again, if you're building 1 million or 2 million vehicles on a platform, every penny counts in terms of costing. Well, yes, it's true that 800 volt system architectures will not cost less than 400 volts. they aren't as expensive as it used to be to spec an 800 volt system architecture. And a lot of that is because the supply base has just caught up with a lot of automakers choosing to go with high voltage systems. The early 800 volt cars, this would be like first generation Lucid Air or early Taycan or even EGMP for Hyundai Kia stuff. A lot of those decisions to go 800 volt really should be commended because there was not a mature, appointed or well-stuffed supply base of AC compressors and lines and ECUs and 12 volt DC to DCs, and the list goes on of all of the subcomponents that need to run at higher voltage. And you can tell that because if you look at early Taycan, for example, they had to have a bus system, a low voltage to high voltage bus system that ran 12 volt for all your electronics, 48 volt for your suspension, 400 volt for the climate control and HVAC, and then 800 volt for the drive systems of the vehicle. And then if you look at generation 2 Taycan, they now just have 12 volt and 800 volt. The suspension systems now run at direct high voltage, the AC compressors direct high voltage, and that is because the supply base has been catching up with more componentry that runs at high voltage. So the cost disadvantage is diminishing. But there are other disadvantages, such as, a clear example is interfacing with legacy charging equipment. And we have a ton, especially in America, of legacy charging equipment in terms of voltage. So every Tesla supercharger installed in America at the time of this recording will not really output more than 490 volts or so. I think 486 is the communicated maximum voltage of a supercharger, which means if you produce a high voltage vehicle, now that a lot of cars have access to the Tesla supercharger network, you need to boost the incoming DC voltage to your battery pack's voltage. And there's three main ways of doing that. There is using a booster box, which is very similar to how Taycan does it. There is going with a split pack where you can configure the battery pack of the vehicle in a series or parallel configuration through a series of contactors and switches, all of which need to pass crash performance and durability and longevity, which is really difficult actually for a contactor to handle, like a 40G side impact without causing a major issue and repetitively still function in the real world. It's not like a pyro fuse that's in there or anything. So this is actually pretty hard engineering to do that, but automakers have figured it out. Or you can use the rear motor's inverter along with the windings of the stator to boost the voltage up. That's very similar to Hyundai Kia EGMP or Lucid Gravity, for example. And there's a bunch of topics to go into there. Regardless of the strategy you do to go to voltage boosting, it adds time, complexity, cost, engineering resources, and then you run into weird bugs, interoperability bugs with DVDT issues, which Hyundai Kias often run into with Tesla superchargers, where, you'll plug in, you'll see the charge session start to ramp, and then essentially there's a delta voltage, delta time issue that causes the session to break. Lucid Gravity, we did a deep dive on that topic with the Lucid engineers about how they circumvented some of those concerns. But this is, when you choose to go high voltage, a lot more engineering resources and time are required currently in the current environment to make that system work really well. There's other issues such as isolation and insulation and frequency interference stuff, but we won't get into too many of those. The advantages are clear, though. There are clear advantages to going high voltage, some of which may be overplayed in the media. For example, the one that always gets me is, you can really reduce the amount of heat loss, I²R losses, by having your current. So if you double your voltage, you go from a 400 volt system architecture to an 800 volt system architecture, all of the power flow losses will not just be halved, but significantly less than halved, because your I²R losses are an exponential basis. And that is true. You're certainly not going to spend more energy going with high voltage. But, I think a lot of people get hung up on those topics when in reality, a wheel and tire choice or a design choice when it comes to a shape of a vehicle have way more of an impact on the overall efficiency than it would from a 400 or 800 volt system architecture in that case. So I would say, yes, that's an advantage. but there are other system-wide decisions that determine the efficiency of the vehicle way more than a lower high voltage architecture choice. The next and real clear advantage that I see with going with high voltage is a charging performance benefit. Now, at the cell level in the battery pack, when we're talking about thermal management of the cell, when we're talking about the cell's charging curve, this is actually not dictated by 400 or 800 volt. The cell is, 2.7 to 4.1, 4.2 volts, let's just say. That's its operating range. In fact, it doesn't really even know what else it's hooked up to in the entire system architecture of that battery pack. The benefit you get from going with high voltage with charging is twofold. The first is you will have reduced transmission losses from the end of the charging cable, or even really outside of the rectifiers inside the charger, because they're outputting high voltage. So through the charging cable into the vehicle and all of the cable heating inside the car, that will be significantly reduced. But also many chargers are amperage limited. So what I mean by that is, in general, most CCS charging stations and even public NAC stations are limited, typically 500 amps. We're starting to see a trend, especially with the Alpitronic Hyper 400 and Delta high power stations, to go above 500 amps, and 600 really is the public maximum amperage you're going to find in our market. Now, if you're limited, 500 amps on a 400 volt system architecture, because again, most charging infrastructure will not output more than 500 amps, you can only charge at a peak of around 200 kilowatts. And that is why Rivians don't do more than 220 kilowatts. That's why, the list goes on and on of many vehicles, Mercedes EQ models, BMW i7, they all kind of do 200 kilowatt charging because they made platform-wide decisions to keep the voltage low. Now, if you double the voltage and you still have a 500 amp limitation, now you can go 800 volts at 500 amps, and instead of 200 kilowatts, you're now at 400 kilowatt charging. And this is why we're starting to see vehicles like the Lucid Gravity and E4 Porsche Cayenne, and the list goes on, of high voltage vehicles hitting sort of that 400-ish kilowatt range. We see the GM 24 module stuff, Escalade IQ, Sierra, EV, that type thing. They're doing like 380, 390 kilowatt charging because they're doing 500 amps at 700-ish volts. They're not quite up in the 800 range to reach that for their battery pack architecture. That's another topic. But that's the main benefit. It actually doesn't have to do with the thermal management or charging curve, but it means you can stuff more energy into the car without an amperage limit. That is also to say, if you go and bring a Tesla Cybertruck to a version 4 Tesla supercharger dispenser today, currently, like I mentioned, Tesla doesn't have high voltage cars, you will see potentially 320 plus kilowatt charging on a Tesla Cybertruck. That is the Cybertruck operating still at low voltage in split pack with just almost, or sometimes over, 900 amps flowing to the Cybertruck, just cranking the current. And that again heats up all the cabling and wires, but does not dictate the charging performance of the truck. So if you have a Cybertruck and you think once you're able to charge at a high voltage charging station, you'll have a better charging curve, the answer is no, or at least not because of the voltage limitations, because the individual cell doesn't know what else it's hooked up to. So thanks for the great question, Colton. So much more to get into. I found, just in that one answer, we could have unpacked 20 other topics, and let me know if you guys want me to dig into more of those and on which particular points. Official Guy Sam asks, why have DC charging costs gone up over 8 times? While commercial electric costs have only gone up 0.5% or so, let's just say 0.5x in this case, over the past 7 or 8 years. Well, it's very true that the commercial electric rates in terms of your per kilowatt hour rate have not increased at the same level that public DC charging costs are seemingly going up. And it depends by region and network, and of course, all of those topics. I think there's a couple reasons why DC charging has gotten more expensive. And the one that I think you're not looking into here, or it didn't put into your question, that really I think is the main driver of higher costs are the billing, I would say the billing side of paying for charging. As an EV driver, I think most of us are pretty comfortable of paying for energy on a per kilowatt hour basis. I go to a fast charger, it's 45 cents per kilowatt hour. That sounds good. I'll plug in, I'll add 100 kilowatt hours to my battery pack, or at least dispensed out of the charger. And now that's a $45 charging session. I think that math makes sense. However, that's not how the charge point operator is concerned about paying for that energy. While they do pay a per kilowatt hour rate, sometimes it's only 3 cents per kilowatt hour, or 5 or 6 or 7 cents per kilowatt hour. What a charge point operator is more concerned about is the peak demand charge and of that station over, let's just say, a month-long period. And typically that would be the maximum power draw of the station over a 15 or 30 minute window, your average power over that period, and you are billed on a per kilowatt basis, not a kilowatt hour, but a per kilowatt of load. And that could be sometimes upwards of $10, $20, or $30 per kilowatt of load on the entire station. So as a charge point operator, you need to go, okay, with this particular location, with this particular transformer size and station demand that I'm pulling from the grid, you have to predict what is your maximum, demand charge. And some of these could be $10, $20, $30, $50,000 demand charges. And then you say, how many kilowatt hours do I need to sell at 45 cents when I'm only paying, 3 to 6 cents to offset that demand charge at minimum, and then pay for, the loan on the equipment that I just paid a couple $1,000,000 for install plus service. And you go, wow, you really do need either a ton of throughput to keep the cost down, because again, what you're really concerned about is selling as many kilowatt hours as possible once you've reached that peak demand charge to offset the cost. And the servicing costs can get crazy these days. So it's really actually difficult to make money as a charge point operator if you are not strategic about your equipment choice in terms of reliability, and maybe even having on-site battery buffer storage or incentivized pricing to encourage higher demand later on in the hours of the day, because demand charge can also be variable by time of day. The list goes on and on. But that to me is the clear driver of back over the last 7 or 8 years, charging was primarily put in by either government-funded organizations or enthusiasts or folks that really just wanted to support the EV movement, maybe weren't out to make that much money. Now that electric cars have gotten so much more popular, everyone knows someone who drives an electric car. DC charging has turned into a business, and it's a tough business to make money at, which means you're just going to see the cost go up. And I think there's no ceiling to how high we're going to see DC charging. I've been to stations that have been $1 per kilowatt hour. I recently charged at a station that was $2 per kilowatt hour. Now that to me just felt like they didn't want anyone to charge there. And of course that would be a, $200 plus charging session on my Tesla Model S. However, there is sort of the pricing model of I'm encouraging EV adoption, maybe in that 20 to 30 cent per kilowatt hour range is on the cheap side. Then you have the next tier of I'm trying to make business by encouraging throughput and not totally screwing over the customer. That really feels like in that 30 cent to 60 cent per kilowatt hour range. And then anything above 60 cents per kilowatt hour to me is just too expensive in today's climate to charge for high powered DC charging. Let me know if you agree with those pricing there. JDZ1 comments and asks, I seem to recall that you charge your Teslas to 50% state of charge daily unless you're taking a road trip. I'm curious why you do that. Is there research backing up this approach? And yes, JDZ1, it's not just my Teslas, but it's pretty much all of my electric cars. I tend to store them between 25 to 35% state of charge. That's where I like to keep my batteries at. However, most electric cars, including Tesla, don't let you set a charge limit below 50%. So I typically go to the low end of the daily range, and that works well for my lifestyle of driving because I typically am moving cars around, and sometimes a car of mine will sit for 1 or 2 weeks, sometimes a month, and there's no reason for it to sit at a high state of charge, especially if it's in a hot climate. And I'm going to insert a chart right here that shows the degradation of the cell and also the resistance increase of the cell when discussing purely storage conditions. And it's broken up by NCA, NCM, and LFP chemistry. And you can clearly see that the higher the state of charge of the cell in terms of storage, and the warmer the temperature that it's stored in, the calendar aging increases massively with those two things. So LFP is the most resistant to this situation, so maybe less important. I still think charging to probably between 60 to 70% daily is overall a great balance of having plenty of range and balancing vehicle health. Typically, when you get above 70 to 80% or above that, you'll have some expansion of the electrolyte in the cell and a few other things that can cause lithium plating and dendrites to form, and the list goes on, especially when we get into extreme temperatures and extreme high power charging. But that's why I charge my cars to a low state of charge daily. But again, as I always say, we're talking minuscule differences here. You could charge your car to 80% every day and it would be just fine. There are many other factors that go into cell aging, a lot of them even determined by the cell itself and when it was manufactured. I wouldn't worry about it too much. I just think if you're going to go on a long vacation, leave the cars down in a lower state of charge, plug them in so that, as they phantom drain, they'll top back up. And it's just good peace of mind. And then I typically suggest a 60 or 70 or 80% daily charging limit, depending on how much of the battery you need. Don't ever let the car limit you. You bought the car for a reason. Don't ever feel like you're having to go out of your way to take care of the car. Electric cars are pretty strong. In general, most people aren't going to keep them all that long, maybe 10 to 12 years at the most. And a battery can handle being charged to 80% daily for 10 to 12 years without much problems. I wouldn't worry about it all that much. Drive protected. Great, Eric, to see Eric here, a good friend of mine. He actually wrapped my Tesla Model S in this really cool colored PPF. So shout out to Eric for doing that. Drive protected on X. He asked, why has Tesla charging speeds gotten worse over the years instead of better? Well, the topic of Tesla charging performance is a big one. I wouldn't necessarily say it's gotten all that much worse. It certainly is not like we're going back to the days of the old Model S 85 packs, which was the long range pack of the time that they got nerfed and the charging performance got really bad. A lot of decisions Tesla makes are unknown. So I would just be speculating by saying, okay, why has Tesla not made charging curve or charging speed a real focus? And the speculation from my side really comes down to primarily cost, but also use case. They probably know that most of their customers are charging at home typically, or don't mind a 20 to 45 minute or maybe even an hour long charging stop. For example, if they're driving a Cybertruck and have to do a deep charge. There's also other reasons. A lot of Tesla charging equipment, version 3 superchargers, just cannot output high amperage for a long period of time without overheating the cables. That, of course, will change with the version 4 dispensers, which use immersion cooled cabling. And I know you're primarily asking about DC charging in this case, so that could be interesting. But in general, it comes down to a cell choice, and there's a few, trade-offs when speccing a cell. What you typically want to look for is a mix between active material and copper. And then, of course, the actual cell material makes a difference as well. But if you think about it in terms of active material, means you can get better cell density, so more range, which is honestly where most people make their buying decisions off of a car, is how far does it say it goes in the EPA cycle on the website versus how fast does it charge. Most first-time EV buyers and even long-time EV buyers, many of them don't care about charging performance. Unlike you and me on this channel, we love high power charging, or at least I do. And so this has always been my dream with Tesla, is to focus more on charging, reduce a little active material. I would take a smaller capacity battery a little bit with much higher charging performance. That's possible. The real trick here is, can you make a cell that has high capacity, high durability as well, but also high copper content and high charging performance at a reasonable cost? Well, that's, of course, the challenge that the whole industry would like to solve. And at least in terms of all the charts that I've seen, and we showed it in the video when we did the deep dive engineering video with the Lucid Gravity, the Lucid Panasonic cell that's going in the new Gravity is a really nice mix between long range and high power charging. Now, a lot of Chinese cars, we've seen megawatt level charging from BYD now. I've shown you the Zeekr Golden Brick charging from 10 to 80 in under 10 minutes. A lot of the Chinese cars have actually made their small battery packs, their short range models, are the faster charging cars. And it totally makes sense choosing between active material and sort of charging performance. So that the trade-off between charging and range. And if you buy their long range model, they actually charge at a lower peak rate, even though it's a higher capacity battery. So there's many factors that go in here, including C rate and many others, but oftentimes it is not the C rate that's determined. It's the trade-off in the cell between cost, durability, high power charging, and energy density for range. And each cell provider is trying to offer the balance that they feel is correct to the automaker. And then the automaker has to take that and put it into the correct packaging decision in terms of number of cells and modules that go into a particular vehicle. And then the charging performance is just one of the thousands of metrics they're trying to hit across the board. But of course, it's something we focus on very heavily here. Back to your original question, why has Tesla charging speeds gotten worse? Actually, I think new Model S and X charge pretty reasonably well. They're not terrible. Cybertruck curve could be way better and has been improved. It's gotten much better, but it's still not great. I think they're just prioritizing energy density and cost. I wouldn't say durability. I actually think Teslas, in my experience, have more degradation than many other cars that I've seen. And perhaps it'll be another question we can get into one day, which is, does high power charging impact the capacity retention of the cell massively? Of course, a little bit, but it's actually not nearly as big as most people think. Some of those really high power charging cars are holding their capacity way better than many lower power charging cars. And we'll dig into the data on that at another episode in the future. Could be kind of interesting. A lot of it's anecdotal, though. Matt Lynn asks, what are the most common things that create thermal derates? Interesting one. I'm talking finite details, battery cells, inlet pins, cables, charging pedestals. I'm also curious on why manufacturers seem to have such a wide range of thermal guidelines for their batteries. Well, there's a lot to unpack there, Matt, and perhaps that's worth a real deep dive episode. But let's start on the thermal guidelines for their batteries. This comes into something called cell characterization. And typically when an automaker purchases a cell from an LG, a Samsung, a Panasonic, a CATL, the list goes on from a supplier, that cell is provided with a data sheet that says, here's how you can operate the cell. Here's its performance. Here's how we know it operates. And that's what the automaker is buying. Again, this is a little bit inside baseball, but oftentimes that sheet that is handed to the automakers of the spec sheet turns out to be either completely wrong or misleading in the application of using that cell in the way an automaker is using it in their total system of a vehicle. And so the reason we've seen a lot of new vehicles launch with conservative charging curves and conservative thermal limits, and then open up over time through over-the-air software updates. We've seen Tesla do it. We've seen Porsche do it. We've seen Mercedes do it. BMW recently came out with a new charging curve for their vehicles. The reason that that can open up is because the automakers are doing cell characterization on their side. I've been in so many automaker labs now where there are rooms dedicated to cycling cells, testing longevity of cells, temperature, resistance, the list goes on and on of the metrics that they're looking for. But that, if you're buying a cell from a supplier, should an automaker really have to go through the entire cell characterization process on their side? Well, the fact that they are tells me and the rest of the world that even the cell manufacturers don't even know the capabilities of their cells to the fullest extent. And so that's where a lot of the guidelines come from. And a lot of new vehicles launch with sort of limited capability, especially because development cycles have been so compressed. And so you just need to get a vehicle to market that isn't going to blow up. So you put all these constraints on it. Once you get fleet data, your own cell characterization, if you care as an automaker, you can improve the customer experience over time. So that's a lot of the thermal guideline questions. What are the most common things that cause thermal derates? Well, are you talking about thermal derating while charging or thermal derating while driving? So let's do driving first and then charging second. So let's say you're really driving your electric car hard, and we've shown this recently in many of our track videos, and I'm sure there will be a never-ending list of content coming with high-performance electric vehicle driving. Well, what are things that get hot when driving an electric car? Well, I'm not going to focus on the typical brakes and other things that are very common in a combustion car that get hot. Tires get hot, brakes get hot. It's all the same. With an electric car, the first thing that typically goes, and it is very specific to each model, the first thing that overheats typically if you're doing a lot of hard acceleration and hard recuperation are the inverters, actually. The inverters to the electric motors are the first things to get huge heat spikes, but they also tend to recover very quickly once you let off. And again, that varies based on the model, the recovery time, the heat time, the target temperatures, the silicon versus silicon carbide rectifiers inside the inverters themselves. All of these are, dependent on the model, but typically when driving hard, the inverter is the first thing to get hot, not the battery. Once the battery gets hot, it has a much longer and slower recovery time because you have so much more thermal mass in the cell. Or of the entire battery pack. And then within the battery pack, you can have thermal derates that happen a little bit quicker if you don't have a uniform cooling system, or if you have a weak group of cells that can create a high point of resistance. You can get something called a hot spot in the battery pack where the cooling system isn't reaching that particular spot, or for whatever reason you're getting one area of heat. Well, you still can't keep ripping on the battery pack if one little area is getting hot, and you're only as good as your weakest link. And so hotspots really can cause a problem when it comes to thermal derating, especially with high discharge power and high recuperation power in a track driving scenario. From a charging perspective, what are the things that cause derates? Well, it's warm outside right now. We're going through a heat wave here in the southeast, and the biggest thermal derating issue I've been running into this week are charging cables and charging handles, but also inlet port temperatures on the vehicle side. There's actually some vehicles that have liquid cooled inlet ports that try to help cool the pin temperatures down on the mating surface, well, at least on the back end of the mating surface between the high power charger and the inlet port of the vehicle. So cables, yes, the mating surface, there's a point of resistance right there, especially with corroded cables that haven't been maintained or cleaned, can really slow down charging. And thankfully it does, because the last thing we want to see is a thermal event happen during the right at the mating surface between a charger and a car. I always recommend when you plug in an electric car, really push the port in there. Make sure you get the great mating surface between the car and the charging handle. I've seen a few videos pop up online of fires happening in the charge port region. Clearly it is an arc or something is happening between that mating surface that is causing a thermal event between the handle and the inlet port. And I would say that's the most common thermal derate right now. There are other issues when charging where things can get hot, such as, battery pack temperature just reaches max, or again, a particular area of your battery pack temperature reaches your max temperature allowed. And then you just have to hope the cooling systems are right sized to either hold it there or bring it down. Many electric cars are not tuned or engineered for high power charging in hot environments with the AC running. I know it sounds kind of weird because we live on planet Earth and it's hot for many months out of the year, and pretty much on any given day somewhere on the planet, it's going to be roasting hot. You would think you would size your cooling systems for where cars are going to be driven, many automakers don't want to spend the money or the engineering time to right-size the cooling systems to give you a uniform charging experience in extreme temperature conditions. I think that's fine for less expensive electric cars. I don't think it's excusable when you're buying a premium electric car. That vehicle should be engineered to operate on the planet we live in, and live on, and the conditions are fairly well known here. So I could go on all day about thermal limitations, but hopefully that answers some of your questions. Dan Birkland asks, what is the magic sauce that allows Porsche to have such an aggressive charging curve with the new Taycan? Yeah, great question, Dan. I've been meaning to do a deep dive video with the Porsche engineers on why they selected that particular cell with that particular system architecture and their particular cooling system. The one thing I will say that Porsche did a great job of is right-sizing their cooling package for their charging performance. They really understand that Taycan owners are going to go on track. Even though it's not a GT3 RS, a lot of Taycan owners go on track, and many of them, including us, want to go on road trips, and you don't want to be waiting at a charging station. The Taycan's magic has always been fairly good high-speed efficiency with incredible charging performance. And the new cell with the new cooling package is, yes, totally unbelievable. The magic sauce that Porsche did comes down to, yes, they're using a pretty expensive cell with a really nice cooling package. It still can get hot and it still overheats. The cooling package in the Taycan is actually tuned for a consistent 200 kilowatts of input or output power with no temperature rise, which means anytime you're charging above 200 kilowatts in the vehicle, you're actually just eating into your temperature buffer until you reach your max temp. Now, what they did is they tuned that cooling system to say if you plug in at a very low state of charge with a reasonable battery pack temperature, just at the point that you're going to hit maximum temperature is also the point that you reach your max charging performance curve right around 65% state of charge, and then it will derate. But oftentimes, if you come into a charging session right off track or off the Autobahn and your battery pack temperature is already up here, you actually may not get that much time above 200 kilowatt charging before you reach your max cell temperature. And then the cooling package, again, is tuned just to handle that constant 200 kilowatt input or output. This is not claimed by Porsche. This is just claimed by my driving research testing of the new J12 Taycan. So they're charging, their thermal management is great, the cell selection is great, and also I think Porsche just knows, like, you know what, you don't really have to worry too much with that cell about charging. They hold up really well from a degradation perspective, and in fact, early Taycans, I'm not going to say they're the most reliable. I'm in the Taycan forums. Some of them have some major problems. Like a lot of it's with intrusion into the battery pack for water and other stuff. Very rarely, actually never, have I heard a Taycan owner complain about battery pack capacity. It's always some other major fault that has bricked the car. But I think that's a really good example to show you can do many high-powered DC charging sessions and not have to worry about degradation. It comes down to the cell, the system design, and the cooling package that allows for great charging performance. And also, I think the effort on Porsche to understand, yeah, the nerds want good charging. Here's a question by Dominic Nachname. Tesla cabin overheat protection. Is it worth it? And is it needed to keep the battery healthy? Living in Atlanta, Georgia. Now, I'm not sure if this has been paraphrased exactly or totally, let's see. Here's his actual question. I had a summarized version. I'm pulling up his actual question, which is: parked outside during the day, taking his wife's Model 3 from 79% to 72% over the course of 8 hours. So he's worried, wondering if should he leave cabin overheat protection on, which is causing extreme, not necessarily phantom drain, but battery drain on the vehicle from running. And I would say it's probably not necessary to run cabin overheat protection. Personally, I keep it off in my Teslas. The way current cabin overheat protection works with Tesla is I believe it's only on for 24 hours after a drive cycle so that you don't get into a boiling hot car. Actually, the screens, the interior materials, the glass coatings, the seals, are all designed to handle very hot temperatures because automakers know cars sit outside baking in the sun. So I wouldn't worry about it from a car's longevity standpoint. It also isn't really going to keep your battery cooler at all. So there's nothing to worry about from a battery protection standpoint. It's really a comfort feature. And if you happen to accidentally leave, I guess, a living being inside the car, they won't instantly melt. I still wouldn't suggest it though, because I've sat in a Tesla in cabin overheat protection. It still gets hot. It's more of a backup fail-safe safety feature. I would say that's the disguise, but it's mostly a comfort feature, so you don't open the door and sit on a scalding hot seat. There's nothing I would worry about from a longevity perspective, keeping it on or off. In fact, keeping it on cycles your AC compressor a lot more, cycles the fans in the car a lot more, and that's just more componentry having to work more of the time. I think that's it for this particular episode, answering 7 of your questions. Again, there were so many. I'm sure we can do more episodes in the future. We can have guests come on that can provide more insight than even I'm able to give you. Again, I'm just learning along with you guys through my journey of learning about electric cars. I don't want to pretend to have all the answers. And of course, if I ever get something wrong, you guys will let me know in the comments below. It is just fun to talk about cars and fun to think about cool scenarios, which you guys are great at coming up with. So I hope you enjoyed the first ever episode of EV Inbox. Do you like the name? Do you like the format? Should I go quicker through my answer? Should I go longer and more in depth? Trying to find the happy medium. You guys know I always ramble way too much. So I want to thank you for your viewership, and we'll see you on another one again soon. Bye-bye.